This is the time integration property proof. We are given an expression that is the accumulation of f of tau from 0 to t is equals to g of t. Once you look at this, actually this is the fundamental theorem of calculus, one of them. In the next slide, we'll remind you what the fundamental theorem of calculus is. We are looking at this second fundamental theorem of calculus, where the integral of a to x ft dt is equal to f of x. And what we are going to do is you realize that this integration, this definite integral becomes a function f of capital F of x. We use capital F of x and small f of x or for a reason, because the derivative of capital F is f of small f. So in fact, we are performing the antiderivative. We are getting the function such that the derivative of f is the small f over here. So this is the second theorem of fundamental theorem of calculus. Now, so if you recognize this, then the left hand side is the antiderivative of f of t. So we are trying to actually get the integration of f of t. So if f of tau, the Laplace transform, this guy has f of s, what is the integration of f of tau d tau? And the surprising thing is that it is very, very simple. It is simply 1 over s times f of s. Okay, so integration becomes 1 over s. That's all in the Laplace domain. That's proof. Alright, so we're going to perform the Laplace transform of g of t, which is the Laplace transform of this little guy here. When we reach this point in time, of course, we can open it up to write the equation for the Laplace, which is, in this case, we are doing the causal. Integrate 0 to infinity multiplied by the function we are interested to perform Laplace transform e minus st dt. Now, once you have reached this point, again, we are going to do integration by parts. And all we need to define is what is u and what is dv. So dv is this guy, and u is this guy. Once we have u, then du is simple, right? So by the fundamental theorem of calculus, if you have u, du is simply this guy, because this is the antiderivative anyway. Now, what then we do is dv. Well, to get the integration of from dv to v is we have to do the integration. So if you do not believe me, all you need to do is perform dv dt, and you'll get minus se minus st over minus s, and then this cancels, and you get e minus st. So this is okay. So we have found what is u and v, du and dv, and we can put it into the equation to solve, which is uv minus integral v du. Now, if you work out the sum, this is what you'll find. Okay, so I'll not explain. I've already written the reasons here. On the left hand side, it becomes 0, and on the right hand side, we will simply have 1 over s times f of s. Okay, that's it. So this is the proof for the time integration property. We will now use the time integration property to find the Laplace transform of t. In fact, you will realize that the differentiation of t is unit step. So there must be, we are actually performing the integration of the unit step to get t, right? So we are using the fundamental theorem of calculus to get this result. And therefore now we remember that we want to do Laplace transform of this guy. We already know that the Laplace transform of u of t is equals to 1 over s. Then the Laplace transform of the integral of 0 to t u of tau d tau is equals to 1 over s. Let's say this is called x of s. What is x of s? Is 1 over s. Therefore the answer is 1 over s times 1 over s is 1 over s squared. That's it. So we have just used the time integration property and the Laplace transform of ut to get the Laplace transform of t.